When we consider position, velocity and acceleration and the relationship between the three, we can see velocity time graphs can be very useful. What I mean by that is when we consider position, which I might call x or s, if I derive that, I get velocity. Furthermore, if I derive velocity, I get acceleration, or from acceleration, if I take the antiderivative of acceleration with respect to time, I get velocity. So if you consider it, velocity is kind of in the middle, and therefore having a velocity time graph can give us just one step to work out position, or one step in the other direction to work out acceleration. So here are some things to look for with a velocity time graph. The first type of velocity time graph that I'd like to look at is a velocity time graph where the line is a single horizontal line. What that means is you have a constant velocity. Now that's meant to be a single horizontal line. There we go. You have a constant velocity. So what that means is whatever the point here is our velocity. It also tells you that the acceleration is zero, because the acceleration is the change of velocity, and you can see as time progresses, there's no change. So therefore, your acceleration is zero. Also, a graph like this will tell you that the area under that graph, so the area here, if you will, is the displacement or the change in position. So if I wanted to find the change in position for this, then it would be V times T is my change in position, where that's T. And when we have a constant velocity, then that area is simply the rectangle underneath the graph for the appropriate length of time. The second type of graph I'd like to look at is where the velocity time graph is a straight line, but it doesn't have a gradient of zero. And in this case, my initial velocity is down here, and my final velocity is up at this level here. Our acceleration is our gradient. I could call that dv dt, or I could call it rise over run. And our displacement, or the change in position, if I were to draw a vertical line down here, the change in position is the area of this trapezium. So again, the area under the graph. Now the area of that trapezium is a half u plus v times t. And therefore we can use a straight line velocity time graph with the gradient of not being zero to still calculate acceleration and change in position. The third case is where we have a curved line on the velocity time graph, and it might look something like this. And if we have a curved line, then the acceleration varies, because the acceleration is the gradient, remember. So my gradient near the start of this graph is lower than the gradient further up. So we have a variable acceleration. We also have a velocity that varies. And therefore we can't use the constant acceleration formulas we looked at in the last class. If we can use our integration, we can find that the displacement, which would be the area under this graph, can be calculated by taking an integral. So the displacement is my area under the graph. And remember, my acceleration is the gradient of the line at any given point. So in summary, my position or displacement or change in position is always the area under the graph. And my acceleration is always the gradient. Now there are three basic cases here in the bottom left that we've looked at in detail, where we have a zero acceleration, a constant acceleration, and then a changing acceleration. And to be able to use each of these basic ideas will help you solve problems and to both sketch velocity time graphs and to interpret information that's presented as a velocity time graph. If you found this or any of my other videos helpful, please subscribe to my channel or like the video. Thanks.